Okay, so we finished the difficult math, more or less. And so this formula here explains, I hope, why if you have an isolated atom, you don't see these oscillations, right? And if you have an isolated atom surrounded by other elements, then you get all these delta psi f, okay? And that's what gives you all these modulations. Okay, now we will go to the interpretation of the oscillations. So we have our nice EXAF spectrum, we have isolated the oscillations, and now we want to analyze this data. So we're not going to do a course on data analysis because we don't have time, but I'm just going to tell you a little bit the principles. How do we do it? The first thing is those of you who have done already EXAFs have already seen this equation. So this is the most simple way to express the chi of k. Now look at this. This chi of k is the same as this, right? So we're going to go from this to this, okay? And I'm going to explain this, what this is. So this is the model that we typically use to analyze our EXAFs. So you see, first of all, there is a sum, okay, over j. So these here are the chi j wavelets that we can write as an amplitude. You have already seen this, the A times the sine of a phase, okay? So here we have the f of k and the delta of k. These are the functions that, contain the information on the scatterer, okay, on what is around your absorber. It's encrypted inside here, and these are functions of k. Actually, the delta and the f are the real part and the imaginary part of the same function. Okay, and as I said, we get these from theory, can calculate them now very well. And if we know these functions, and we do know them from theory, we can determine, so we put these and these are known. We can use this as a free parameter, this is a free parameter. We can use r as a free parameter, and we can get these values by fitting our data. Typically, this is englobed in f of k. The mean free path is also calculated by the programs. So now we're going to try and, let's say, retrieve that function, this one, okay, starting from here, okay, for the very simple system, which is this simple system here, where we have only two atoms. We have an absorber and we have a scatterer, okay? So we divide all space into three parts. We have part 1, region 1, which is a spherical region, spherical potential. Region 2, which is a flat, constant potential. And region 3, which is again spherical, because here we have a nucleus, we have another nucleus here. So, and then we have to calculate that function that you saw before throughout the different phases. So we start from psi 0f, so this is the outgoing wave in region 1, so that's the amplitude of that wave here. And then we add this part, which describes the phase, okay, because we're going to use a spherical wave. This is the analytical expression for a spherical wave. It has a phase, and it has an amplitude which decreases as you go, far away. So we write it here, and we put here, instead of little r, we put big R, because we want to calculate it at the border right here. Okay, so this is the amplitude of the wave when it arrives. Sorry, we put big R, because when it arrives on B, right? Okay, because when it arrives on B. So we put little r is equal to BR. We multiply this by a phase shift, because this is the phase shift that the wave undergoes when it goes out of this spherical potential. Every time that there's a change in potential, we have to add a phase shift, which actually takes into account this change. So this is the propagation, phase 2. And then when we get to region 3, we scatter. So this is where we get the amplitude and the phase of the scattering atom. And then, in order to detect it, remember, it has to go back. It's scattered, so it has to go back. So again, it has to propagate this distance backwards. Again, it's a spherical wave, which propagates r. And again, it has to enter again into this potential. So it undergoes again a phase shift like that. If you multiply all that, you get this. Okay, you can try it at home. You will get what this looks like this. Where delta is the scattering phase shift plus twice the core, the central atom phase shift. Okay, so that's for one atom scattering. Now, if you have n atoms at the same distance r, then you just multiply this by n because they all scatter in the same way. They're all identical atoms. They have the same F. They have the same R. And here, we are putting this distribution function which takes into account the fact that they're not exactly at R, but they are distributed with a certain distribution. Let's take a simple Gaussian distribution. And so we get this exponential which takes into account the fact that the distances are all not exactly R, but they have this distribution. So there's a little bit of disorder in this shell. Now, in a real system, we will have neighboring atoms that are at different distances, and they're different types. So we put a sum over J, where J tells us the type of atom, which have a different F. Each of those will have a different F. They will have a different R. So these are different shells at different distances. Each shell is the same kind of atom, but they have many shells. And as you know, we're lucky because we don't have to put too many. We can put maybe 1, 2, 3, and the others don't count. That's what allows us to do this analysis simply. So to get this formula, we have used the expression of a spherical wave. Okay, remember in the previous slide. Now, the problem is that in reality, as I told you, these photoelectrons, as they travel, they also lose energy because they can interact with plasmons. They can excite excitations, and they can lose energy. If they lose energy, they're lost. They do not participate anymore to the interference. And so we use this, this term here, this damping term, you see, which depends on the mean free path, that you know what it is, because we've already seen this. And so this takes into account the fact that you will never see shells that are very far, because this thing here is going to kill that amplitude. Okay? And so this is what you get. So the fact that you have lambda, mean free path, which is very short, and the fact that you have r squared on the bottom makes EXAFS a very local probe, very, very sensitive to the first shell. So I always say it's really short-sighted. It sees the first shell very well. It can really give you precise values for these distances. It can tell you what you have in the first shell. It can tell you very precisely the disorder. But as you go already to the second shell, it's already quite blurred. Errors are much bigger, and if you go to the third shell, it's even worse. So this we've already seen, so we can go quickly. This is something that you will always have in your analysis. We put it at the beginning. As I said, it can be 1 in the best of cases when all the other electrons, nothing happens to them, but we know that they do rearrange a little bit. So this is always a number which is a little bit less than 1. Now the problem is with this S0 square is that if you look at the equation, let's look at this simple equation. S0 square multiplies n. These are two numbers. They have no k dependence. There's no way that you will ever be able to determine these two numbers independently. There's no way. You can only determine the product of these two numbers. Okay? So when you do an EXAFS analysis, typically you don't know what this is. So you first do an EXAFS measurement on something, which is your reference, where you know n. So you fix n, and you find S0 square. And then you use that same S0 square to look at the real unknown samples. Of course, you have to be looking at the same edge, because S0 square is an atomic property. And if possible, at a structure which is sort of similar to what you're looking at. Okay, so now I'm going to say a few words. Yes?
So what if you get S0 wrong? How big of an impact will it have on your analysis results?
Typically, it can go up to 20%. So coordination numbers can be affected by relatively large errors, whereas the distances in EXAFS are much more precise. They can go up to 1% or even much better if you're doing a relative comparison. Okay, I'll say a few words of Xanes. Normally Xanes is, I could talk for hours on Xanes, and there's really a lot of information you can get. And very often, in difficult situations, it's the only signal you get. Because EXAFS is such a small signal that if you're in difficult situations, high temperatures, high pressures, dilution, very fast experiments, you just don't get the EXAFs because the noise is too high. But the Xanes, you typically always get something. The problem is, as I said, that it's not so simple to analyze because this photoelectron just lives forever. And so you would have to put a sum over 1,000 paths to explain all those features, and we can't. I'm just going to say a little, I'm going to show you some examples to just give you a feeling of the kind of information that you can get. Yeah, so I'm going to show you the example of transition metals again. So the K-edge Xanes of a typical transition metal oxide like a manganese 3 plus ion in a manganese oxide. So this is what the Xanes look like. We can divide it into 3 parts. So this is the electronic configuration of this ion. So when you excite a 1s electron here, you go into this case at the very beginning. So you see, you don't have enough energy to free the electron, so the electron is not in the continuum, but it just occupied the first possible available state. Okay, because you only have 4 electrons, so there's 2 holes here, and so the first thing, it goes there. The intensity is very, very low. Why? Because this is a delta L equal 2 transition from S to D. So it's dipole forbidden. You know this now. Okay, dipole selection rules means delta L has to be equal to 1. So this is a very low intensity, but it's there. Now, if you go to a little bit higher energy, then you can go to p states, the 4p, and even higher, the continuum. So these are continuum states with p symmetry. The intensity is much higher because these are dipole allowed. Okay, so this is the main edge, and this is the continuum. So this tells you what you're looking at when you're looking at the Xanes. Now, we are very sensitive to the chemical state of this ion, and I'll show you an example. If you look at Mn4+, you have 1 electron less in the D band. Okay, what does this mean? This means that when you go to this 4p state, the screening of the nucleus is less efficient because you have 1 electron less. And so you need a little bit more energy. This is at a higher energy, okay? Because the screening is you see a bigger positive charge. So you have to go a little bit more. So you can look at the shift, and this shift will tell you whether you're looking at manganese 3 plus or manganese 4 plus. Okay, so that's one thing. You can look at the valence. It tells you about the valence. Another thing is if you look at the pre-edge, so remember these are this region here just before the main edge, the dipole allowed edge. Here, we're looking at transitions to the D states. Here, this is the valence band. Now this region here can tell you a lot about the symmetry of the absorber. So for example, these are 2 chromium compounds, chromium 6 plus and chromium 3 plus. So they have a very different pre-edge. And why is this the case? Because in chromium 3 plus, the chromium is in an octahedral symmetry. So this is a centrosymmetric structure. Okay, so the 3D orbitals, you know, they don't really feel the 4 P's. They don't interact much, right? So you're only seeing actually the 1s to 3D quadrupole channel, and that's why you have a very small feature here, because it's dipole forbidden. However, if you distort the structure and you go into a tetrahedral structure, this is non-centrosymmetric, here you have very strong 4p 3D mixing. This is hybridization between 3p and 4p and 3D hybridization. And this hybridization that you need to make these bonds gives the D levels a very strong p character. And so the intensity goes up because you start having dipole allowed transitions to the p states. It's a bit complicated, but just imagine that when you have something which is non-centrosymmetric, you have very strong hybridization with p, and p are dipole allowed. And that's why, so if you look at the pre-edge, you can immediately say whether you have a distorted site or whether you don't have a distorted site. So this is another kind of information that you can get. This just shows you different iron oxides. So this is the metal. So this is Fe0. This is Fe2 plus. This is Fe3 plus. And this is an intermediate one. And so you see the edge shifts with valence. Now for the iron oxides, it's very nice. It's almost linear equation between the valence and the edge position. So let's say the maximum of the derivative of this jump. However, this is not always the case because, as you know, I mean, all these structures are not determined only by, you know, the energy levels of these states, but there's also information coming from the different scattering paths, right? The structure. So since the structure in different oxides is also very different, that will also affect these features and therefore also a little bit the edge position. Okay, so you see these features are all different because the structures are all completely different. So you have to pay a little bit of attention. In iron it works well, but in other systems it might not work as well. So typically xanes, well, when you have an unknown system, what you try to do is you try to measure as many reference samples as possible. So things that, you know, if you have, I don't know, a mineral and you don't know what it is, you try to measure many similar minerals and you try to use a fingerprinting sort of approach. You measure many different xanes and then you try to do linear combination or things like that. This has been done for many, many years. Now we're more moving towards different approaches because the theory support is much more solid than it was 20 years ago. And so we use a lot theory to sort of guide us in these kind of analysis. And the simulation of xanes is also becoming something which is, let's say, more, you can simulate much better now the features of xanes than we could 20 years ago. Although it is very complicated. Yes?
When you choose the reference materials,
yeah.
Are bond length important, or is it more the chemical species of the
Yeah.
neighbor?
Actually, it's more the chemical species because the bond length will give you a scaling of the whole thing. But the chemical species and the position of these atoms with respect to, I mean, the bond length in general, I mean, then you can compress or expand. But it's the geometry of how they are bonded which is important. Not so much the value, the absolute value of these bonds. Because that's what determines the shape of these features. So to do a calculation on xanes, you need to do a full multiple scattering analysis. So you have to put all the possible paths. So we have now codes that do this. So just to conclude, the interpretation of the xanes is complicated because you cannot use the Xav's equation because it breaks down at low K. So when you get close to the edge, it breaks down because this photoelectron lives forever. We don't have a simple equation for xanes like we do for the Xavs, but you can interpret it in terms of, you know, band structure, symmetry of the side, and so on and so forth. At the end, the question that you ask yourself is, what are, you know, the electronic states that the photoelectron can fill? Where can it go? Okay? Yeah, exactly. For example, is there a hole in the 3D states, or is there a hole in the 4P? That's what's going to determine the shape of your xanes. As I said, quantitative analysis using first principles are quite rare, but things are evolving very quickly. And here I just want to show a slide that summarizes a little bit the attempts that we're doing on the theory side to simulate these spectra. So you can use different approaches. There is the multiple scattering approach, which is what is used in FEF, FDMNES. These codes are very useful for systems that do not have very high electron-electron correlations, like metals. So these work well for metals. If you have very strong electronic interactions, then you better go with a model like, model Hamiltonian, where you can do also multiple calculations. But there's also other approaches that are sort of like a mixture of both, and so on. I'm just saying that this is a field which is evolving very, very quickly with more and more codes, and so it becomes more easy to analyze even the xanes. Conclusions: xanes is a much larger signal than Xavs because you see an edge. Okay, sometimes you just see the edge. It's easier to crudely interpret than the Xavs because if you see a shift to the right or to the left, you already know more or less what's going on. But it's much more difficult to fully interpret. If you want to know exactly what all those features are due to, then it's much more difficult. Okay, now I have how much time? It's 4:20, you have to finish at 4:40? 5:40. Ah, okay. So we have a lot of time. Good. Maybe I went too fast. Okay, examples of applications. So we have a lot of time here. Oh, but we have to stop. When do we have to stop? I'm so worried about stopping.
We have to stop at 45.
At 4:45? Okay. So remind me if I forget. Examples of applications. So, yeah, we still have a little bit of to do. So what are the applications that you want to do with X-ray absorption spectroscopy? Well, let's see what are the advantages with respect to diffraction methods. So typically, you use diffraction methods when you have an ordered system. You can use neutrons, you can use X-rays, but you need something which is ordered, long-range ordered. And there, these are extremely powerful, as you know. You can get the three-dimensional positions, in 3 dimensionals of all the atoms in your sample. But if you have atoms which are intrinsically disordered, systems which are intrinsically disordered, like amorphous solids or liquids, then these methods typically only give you the one-dimensional distribution function. And these radial distribution functions contain interactions of all possible atomic pairs in your system. And so, it just becomes a little bit more difficult to disentangle the information. If you use X-ray absorption fine structure, then you always get a one-dimensional distribution function, but it is centered on the absorber. So that already simplifies a lot the situation. Okay, so if you have, for example, A, B, and C atoms, if you do diffraction, you will have AA, BB, CC, AB, BC, AC, everything mixed. If you have exafs and you look at an ABC system, you will only have AA, AB, and AC. So that's already simpler. You know where you are, you know where you're sitting. Then you also have electronic sensitivity, sensitivity to the charge state. You are very sensitive to the local structure. Okay, so the nearest neighbor, you can get that with very high precision. And then, as I said, if you get very good data, you can get information on triangles, distribution of triangles. That's something that you cannot do with diffraction. Okay, so typically applications are when you need element selectivity. So for example, you're looking at a system which has many different elements, and you want to look at the environment of only one of them. And this could be something that can bring you some information. Electronic structure, local structure. So typically, exafs has been used to look at non-crystalline matter, amorphous systems, the environment of an impurity in a matrix that has completely different atomic species. To look at systems that have local properties which are different from the average, so systems which have big distortions inside the unit cell, for example, and also very, very small distortions. So I'm going to show you 2 types of applications. I'm going to start with showing you 3 examples of major historical exafs breakthroughs. So the reason why I want to talk about this is because sometimes you lose a little bit, the history of how these things have evolved. And exafs actually was first observed at the beginning of the last century, like beginning of the 20th century. You know that we had Bragg and Laue, they had Nobel Prizes in that period, a few years after the X-rays were actually observed. At the end of the 19th century, the beginning of the 20th century, we had Nobel Prizes for Bragg and Laue. And very soon after these big events, people were already seeing in photographic plates exafs oscillations. They were seeing an image which showed oscillations in light of a dispersed, energy dispersed beam. And these oscillations were exafs. And they tried to interpret them with theory. But the data was so crappy that the theory didn't advance. And it was only in the late 70s when we started having synchrotrons, which could give, relatively good data. That's when the theory really took off, because you had data to which you could compare the theory. And so in those years, in the 70s and the 80s, exafs started to be used, and it solved really, really, let's say, important problems that people were stuck with at the beginning. And I'm going to show you 3 examples of those problems. And then I'll show you a selection of recent results that we have today, for example, at synchrotrons like the ESRF or other synchrotrons around the world. So we start from these EXAFS breakthroughs. So these are the ones that I picked. One is the atomic scale structure in solid solutions. One is the lattice distortions in impurities, around impurities and dilute alloys, and the other one is the structure of amorphous materials. So these are three things that people really had a lot of questions about, and when EXAFS came to be used as a quantitative tool, it was able to solve and answer these questions. So this is one of the first papers in the early 80s where they looked at the structure of these solid solutions. So these were semiconductors. A lot of people were working on these. I was working on these too in that period. I'm very, very old actually, you see. I was already doing well. Not really in that period, a few years later. But these are solid solutions where you have a mixture of an AC compound and a BC compound, right? So you have a sublattice, which is a mixture of B and C atoms, A and B, sorry, atoms. And then you have the other sublattice, which contains only C atoms. And at the time, the atomic scale structure of these systems was not well understood. So you could do diffraction, and you could measure the lattice constant of these systems. And when you changed X, going from AC to BC, you could see that the lattice parameter was also going from the lattice parameter of AC and BC. So it was more or less linear. But people wanted to know the near neighbors distance between A and C and B and BC, and that they couldn't measure with diffraction. So often they were using approximations that told them that these positions were more or less equal to each other. So AC and BC were equal to each other and were equal to the values in the parent compounds. So I added this to make this more clear. You see, AX goes linearly from AC to AAB. And the interatomic distances here are given by this very simple function, and here as well. And so they were using, at the time, the so-called virtual crystal approximation that was saying that they had no clue where these atoms were sitting. But they were saying, well, they're sitting exactly in the same atomic sites as the parent compounds. Okay, so they were using exactly the same expression, which means that these distances were equal to each other. And they were using this to calculate, optical conductivity, thermal conductivity, reflection, and all this. And something was wrong. I mean, it wasn't working, because this is a very wrong approximation, but nobody knew at the time. And so these people did the first measurements. So they did the arsenic K-edge in these systems, and they measured the arsenic indium distance and the gallium arsenic distance as a function of x. And you see the virtual crystal approximation says that these two distances are equal to each other. And actually, look how different they are. So instead of falling on this line, they're completely different. They're very close to the distance in the parent compound. So indium arsenic, wherever it is, if it's in indium arsenic, or if it's in just one atom of indium in gallium arsenic, it always has more or less the same distance. So the bonds are really strong. Okay, so this really showed, so this was one of the big, discoveries of EXAFS. It was able to measure distances. Until then, this was not possible. And then they understood why everything was so weird and not working, because the structure of these systems is completely distorted. It's not at all as they thought. This is another mystery that was solved. So at the time, people were doing, these fiber optics. They were putting a little bit of impurities in something. Well, fiber optics, this is another application. Metals, they were putting one dopant or very, very small amount of manganese, for example, in nickel. And then they were using these to do whatever application. And obviously, they didn't know what was happening to the local structure around the impurity, because they couldn't measure it. So they were just assuming that, when you put a little bit of manganese in nickel, well, it just substitutes a nickel atom. That's all. So the distance between manganese and its nearest neighbors, well, they were assuming it was exactly the same as the distance between two nickel atoms. And EXAFS showed, this was, in the 80s, let's say, this was published in the beginning of the 90s, that this is not at all true. So they could measure, you see here, the manganese K-edge, it's this very small signal because this is not much. They analyzed the Xray oscillations, and they were able to find, with very high precision, the distance between manganese and nickel. So that's their Xray signal multiplied by k square. They Fourier transformed it, and they looked at this peak, or this wave, right, which looks like this. They fitted it, and they find that actually when you put a little bit of manganese and nickel, it really shifts the nickels, the first shell, a lot. I mean, this is 1%, which is huge, actually. And with this information, they were able to understand a lot why, when you put just a little bit of something into something else, the properties change a lot, and why they had these, this evolution. So immediately after these first works, you see, once you start being able to measure something, then you really trigger the theory behind. And what happened is that in these years, people were starting to use ab initio methods, band structure calculations, to calculate properties, atomic properties. And you see, this was an experiment where they measured the displacement of the first shell of many different elements in copper. Okay, so you see, of course, copper is 0, because copper and copper doesn't change anything. But if you put nickel, you have a contraction. If you put cobalt, you have a contraction. If you put a little bit of titanium, you have an expansion. Okay, and they did this for this whole number of elements. And then they found these are the triangles. So this is the data that has this very funny behavior. And then the fact that they could measure this allowed the theoreticians to do a theory and to explain why this has this evolution. And that's where you really start understanding what's going on. Because the theoreticians were able to reproduce with their theory exactly the same behavior, but they could do it only by adding two effects. One, which is this sort of parabolic shape, which comes simply because you have a valence difference. Because when you put, for example, nickel into copper, you have 1 electron less. And so this change in just the valence makes it so that you have a contraction. So this explains this sort of behavior here. But when you go here in these elements, this is not enough to explain what's going on, because the measurement told them that you were not sitting on this curve, but you had distances which were larger than the curve that you would obtain if you only considered the valence. And so they understood that in these elements, which are chromium, manganese, and iron, you have to add a magnetoelastic contribution. So that's when they started understanding that these magnetoelastic contributions are actually very important, because these systems have a very large magnetic moment. Okay, so they have a low density of states at the Fermi level, which means a low binding energy, and that's why the distances are bigger. Okay, so that's when you really start understanding what's going on. And before Xray, you could not do this sort of fine analysis. And finally, the last example is the structure of amorphous materials. So in those years, people were starting to use silica, SiO2, to do everything. Okay, everything was, I mean, as I said, fiber optics, but also, you know, a lot was being used more and more for supports for different electronic things. And so everybody was interested in understanding the structure of silica, the structure at the atomic level, because if you don't know the structure at the atomic level, you cannot reproduce its properties. And there were two sort of possible models that could explain the diffraction data that they had, because they could do diffraction. And so with diffraction, what they saw is they saw, you know, some sort of blobs. And they said, well, we can explain this either with a random network model. That means, well, here we're looking at germanium O2, which is an analog of SiO2, because silicon is very difficult to, Xray at silicon is more difficult to do than germanium, so they were looking at germanium. And so this model was saying that the tetrahedra in silica or in germania were actually connected, so you still had tetrahedra, and they were connected to each other by angles which were sort of wobbly, very big deviations, but you still had locally one germanium surrounded by 4 oxygens in a tetrahedral configuration. But you would not see sharp peaks because they were not observing sharp peaks, and you don't see the sharp peaks because each tetrahedra is connected with a different angle. So very quickly you lose the long-range order. The other model was the macrocrystalline model. That means that you have locally an ordered structure. You have a crystal, but it's very, very small. It is so small that you see very big blobs in the X-ray diffraction. Okay? You don't see sharp peaks because the local order is very small. But this model means that you had crystallites of the order of 15 to 20 angstroms. So you had many, many tetrahedra, because one tetrahedra is about 3 angstroms big. You had many that locally up to about 15 angstroms were forming a little crystal. They're perfectly ordered. And so they did EXAFs here, and what did they find? They did EXAFs at the germanium K edge. And look what they find. This is the Fourier transform. So it looks really horrible because at the time they were not able to subtract the background properly. But this is the first shell, and this is the second shell. So they measured it on crystalline GeO2 and on glassy GeO2. So you see they measure exactly the same thing in the first shell, but in the glassy GeO2 they see no second shell. Okay? So this automatically eliminates the microcrystalline model. Because if you had microcrystals of a dimension of 15 or 20 angstroms, then of course you would see the second shell. The second shell is at 4 angstroms. It's at 3 angstroms. You would see it. It would be very, very ordered, and you would see it, but they didn't see it. So it's a very simple analysis. Just by looking at the data, you can tell. But, you had to have this technique to get this answer. Okay, so that was the third one. So we stop here? No, what time do we have to stop? 45. Okay, we can do a little bit. So now I'm moving fast forward 1 century. No, we go to the next century, 21st century. So I'm going to show you a little bit of things that we do today. Most of these examples come from the ESRF, but not all of them. I've picked also some things from other synchrotrons. So I will start by saying a few words on the different kinds of spectrometers that we have here, also at other synchrotrons. Okay, we have energy scanning or energy dispersive spectrometers. And then I have put together a number of examples. I'm not maybe going to show all of them, but I will stop at some point when we have to stop. Because I know that a lot of teachers talk too much, and that makes you very nervous, right? Because I was one of you, and that was very annoying when people go on and on and on and they never stop. So I'm very careful about this. Okay, so we have different kinds of spectrometers. So up to now, I only talked about this kind of spectrometers. So this is the simplest kind. You have the synchrotron, you have X-rays which come out with a very broad energy range, and you want to select one energy. So use a double crystal monochromator, for example. It gives you a monochromatic beam. And then you scan the angle of these crystals so that you go through all the energies. And you see these are all the beam lines that we have. They're practically all scanning, all of them, except for one. One of them is energy dispersive. So this was the first beam line I was in charge of. When I was first recruited by the ESRF in 1997, I became responsible for this beam line. And so this is different, you see. Well, the optics is much more complicated, but I'm just going to explain the principle. So you have a source that comes in, and you have a large divergence. And then you have a curved crystal. So every single beam that hits a different position will be diffracted with a different angle. So the diffracted beam has different energies, okay? Because you see, this angle is bigger than this angle, so this energy will be lower than this energy. So this crystal, since it is curved, it will also focus the diffracted beam, and so you can focus it on the sample. And then after the sample, you can put a position-sensitive detector, so you can measure at the same time all the energies in a bandwidth. So if you make the bandwidth large enough, you can actually measure the full absorption spectrum in a single shot. So this beamline here has been really developed to do very fast time-resolved stuff. So chemistry, chemical reactions, whatever, very, very quickly. And let me see. okay, since now I'm at European XFEL, very fast has really a very different meaning for me now than what it had when I was here. Very fast here means that we can use the pulse, the bunch length of the synchrotron, which is typically 100 picosecond, let's say, and that is our limit. So if we're able to do an experiment with just 100 picosecond of photons, that's as fast as we can go here at the synchrotron. At the XFELs, and I'm going to give you a tutorial tomorrow about that, we can go much faster. But being able to do an absorption spectrum in 100 picosecond was absolutely not obvious. But we managed to do that here at the SRF, and I'll show you some examples. So that's the limit where we can get. That means that we get sufficiently good data with a single bunch to get something that we can actually analyze. Okay, so we have these very different spectrometers. So here we have a lot of IDs, means undulator beamlines typically. We don't have many wigglers here. So they're all very specific. So ID12 does polarization dependent absorption spectroscopy. ID26 is optimized for high brilliance. They do a lot of emission spectroscopy, resonant and elastic X-ray scattering, RIX, absorption too. ID32 is the soft X-ray RIX that I showed you, the big red spectrometer, soft X-ray. ID21 is micro and nano spectroscopy. They do a lot of imaging. ID16B is what? I can't remember anymore. ID16B. I think it's another, I can't remember. And then we have a lot of, we have BM23. BM23 is a bending magnet beamline, which is a very standard general purpose exhaust beamline, which I was also in charge of. So I became in charge of this beamline in 2000. So I had two beamlines, this and this. And these two beamlines were very, very different because BM23 was a very simple beamline with huge user community and doing really, really, really good science and publishing a lot and extremely oversubscribed. This beamline here is the simplest one of all, and it was the one that was the most asked, the most oversubscribed. ID24 was very specific. You know, we were doing very difficult experiments. Most of them were failing. Sometimes we were able to do something which worked, and then we had to repeat it at least 3 times to really make it work. The community was very small, but we were doing, you know, really, really unique things. But you could, it's really important to do both in a facility. That means something like this will really push the possibilities of the methods that we do. For example, the fact that now we can do a spectrum with just one bunch, right? This is really special, and we can do it on I-24. But you really, really, really need beamlines like this that really produce a lot of science and get the community here. And then we have many CRG beamlines. These are beamlines that are funded by external groups. So we had an Italian CRG, BM8, which is now called LISA. When I came to the SRF, I was actually in charge of this beamline. I was there when we constructed it, we commissioned it, and it was called Gilde at the time. Then we have Swiss-Norwegian CRG beamline. We have German beamline, Spanish, Belgium, French, etc. So many, many national institutes that come here, they pay the staff, they finance the beamline and everything, and ESRF provides X-rays. And in exchange of the X-rays that the ESRF provides to these groups, they have to provide a little bit of beam time to our users, ESRF users. So when you apply for beam time at ESRF, you can also get beam time on the CRG beamlines for 30% of their time. This is the way they pay back the fact that we give them beam time and they can use it for 70% for whoever they want. Okay, I'll stop here and then we start with the examples. So we can go and have coffee. If you have any questions. So we come back at, let's take 10 minutes. Okay, so let's continue. We have half an hour left, more or less. So we'll go through some examples. You must be quite tired, but the lesson that comes after me is very, let's say, it's really cool. I mean, you don't have to, you know, think too much, and it's going to show a lot of nice images. So it's going to be a good evening talk. So even this is much more like a seminar. It's not too much like a lesson. We'll just go through some examples. So it's going to be a little bit more, let's say, less heavy. So the first example, this is work on ID24. So as I said, this beamline is really focused on doing time-resolved studies, and one of the big areas of application is catalysis. And so we did a lot of work here with many, many people that came and went, I mean scientists, postdocs, to set up a combined experimental facility where you could measure at the same time, with the same time resolution, the structure using EXAFS, the reactivity using mass spectrometry, and the functionality using infrared spectrometry. So everything is mounted at the same time on the beamline, and therefore you can really get a lot of additional information than just EXAFS. And you can correlate the information you get with the EXAFS because you can measure everything at the same time. So this was an example where we're looking at 1% palladium. So I'm not a chemist, so forgive me if I say stupid things. But okay, this is a palladium catalyst. It was 1% palladium in, I can't remember, maybe alumina. And it was looking at these redox cycling reactions. And so if you do the palladium edge, you can see when you form clusters because you see a big palladium peak coming up, and you can see when the palladium is oxidized because this peak disappears, and you can see more oxygen nearest neighbors. And so you could follow this on the time scale of, this was seconds. And then at the same time, we were looking at the infrared spectra, which tell you about the molecules that form on the surface of the catalyst. And so it tells you about the activity of the catalyst. And mass spectrometry would tell you about the gases, where they, what kind of gases are formed. And so when you put everything together, you can make models like this, okay, of the whole catalytic cycle. So this, the fact that you can do, and you can look at the reaction from different points of view, is really very, very powerful. This is another example which summarizes a little bit the work we did with Toyota. So Toyota came for 5 years at the beginning of 2000. So they stayed from 2002 to about 2007. And they were interested in optimizing the catalysts that we have in the cars. So these are so-called three-way catalysts. So the big problem, so as you know, the car, we have the engine, which produces a lot of toxic gases like N2O is not good, or NO also is not good. And we have boxes inside the car that take all these toxic gases. You go through this box, and you come out with things which are more or less environmentally friendly, like, for example, nitrogen or CO2, which is a little bit better than CO, right? CO is very toxic. And oxygen, of course, right? And water vapor. So what do you have in the box? You have a sponge, and on the sponge, you have a sponge because you want the gas to go through the sponge. And on the surface of the pores of the sponge, you put little metallic particles, nanoparticles, very, very small particles, but are typically particles of very expensive metals like platinum. Platinum is really expensive because we don't have much anymore. We've been completely, exploiting our soils, and it's more and more difficult to find platinum or gold or palladium and these very, very expensive metals. And so the problem is that when these little, so they are very small. Why are they small? Because the smaller they are, you see, you have to imagine these molecules of gas, they go through the sponge, and they have to touch the metal so that the metal catalyzes the reaction that transforms, for example, N2O into N2 and oxygen, for example. It has to touch the metal because that's where the reaction occurs. So the problem is that when you are in this very close to the engine, temperatures go up very much. They can go up to 1,000 degrees. And so these little clusters, they move around, and they become bigger and bigger. They sinter. And when you have a big lump of platinum, well, you're actually not using most of your platinum, because if it's inside the big lump, it's not in contact with the gas molecules. So you're wasting it. So they did a lot of, everybody's working, all these car companies are working on the same problem. Avoid the sintering, avoid clustering of these things. So they have to block these tiny particles, they have to block the mobility at very, very high temperatures. And this is a hard thing to do. And they work a lot on the nature of the sponge. And these sponges are typically oxides which contain rare earths or complicated things. Okay, so they came with hundreds of different sponge. I call them sponges, but they're sort of supports. They can be zeolites, they can be, let's say, porous supports. And we could measure very quickly on ID24 the platinum L edge in these systems as a function of time inside something that looks like a reactor. We actually constructed a catalytic reactor and we put it on the beamline. So we could measure the platinum L edge while the catalyst was working at very fast speeds. Okay? So you see they were cycling exactly as it happens in the catalytic converter. They were cycling oxidative and reducing atmosphere really, really fast. And they were looking at the surrounding of platinum. And they were able, by doing these experiments, to find the right sponge, the one that blocks these little clusters and avoids them moving around. Right? So this was a really, really big discovery for them. Because that made a big impact, and they started selling these catalysts now. So they're all in your cars. This is another example, this is work done at SACLA. At Spring 8. I show this because, I mean, this is really, they have a very small spot. So they have a few, hundreds of nanometers. And they are able to look at the oxidation state of, I think this was cerium, in these little tiny particles as they undergo a catalytic cycle. So there again, they're fluxing, but as the catalyst is working, they do a full map, okay, with this spatial resolution. And they can see how the electronic state changes on cerium. Okay, and then they can plot the different stages of the catalyst. So I thought this was really, really good because not only they have a very small spot and very high spatial resolution, but they also can do this during the reaction. This is another example, again, of operando. So this is, a lot of people now are working on batteries. So here, this was L-edge nickel. This is done in the US at ALS. So here they're looking at a battery using soft X-rays, and they're looking at fluorescence, so on the surface, and they see how this is the L-edge of nickel, how it changes shape as you charge and decharge the battery. So how, as the electrons move in and out, you can actually see it on the data. And they can follow the charging and recharging, and they can see what effect it has on the material. And this is also similar work, but this is at the K edge. So look at the difference in resolution. See, the L edges are very nicely resolved because the intrinsic core hole broadening is much smaller. And here, this is more of a blob, right? But you can still get some information as the battery charges and discharges. You actually see the shift and the moving of the electrons from one side to the other. This is a nice example, which I like to show. It's really old. This is stuff done on BM29. So this was, because before this bending magnet beamline, the standard EXAFS beamline was on BM29, and then we moved it in 2000 and, I can't remember, 9 maybe, we moved it to BM23. So this is very old stuff, but I think it's interesting, especially for those of you who do biology here. Anybody? Yeah, some of you. Okay, why is this interesting? Because here we're looking at a complex which has iron, and then it has carbon and nitrogen. Now, EXAFS has a lot of trouble in distinguishing light elements which have only one electron difference. So carbon, nitrogen, oxygen, it's very difficult by doing an EXAFS measurement only to know whether you have here carbon and nitrogen, or nitrogen and carbon, or oxygen and nitrogen. It's very difficult. But with this paper, they used a new method that allows to simulate the xanes of very simple molecules, because it's very difficult to do simulations of xanes. And they used xanes and EXAFS together, and they were able to actually identify with very high, let's say, reliability, what are the scatterers. So just to show you, you see here are the xanes, and here are the fits they did with different, okay, they knew what they were looking at. Okay, this was just a test example. They knew that it was CN, but they tried fitting it with CO, so they left the right first shell, and they changed the second shell from nitrogen to oxygen. And then they changed even the first shell. And you see that the fit is much worse, and you can even look here that let's say the reduced chi-square, so the goodness of the fit, is better when you have the good atoms. And so this was really the first paper that showed that you can fit xanes in a quantitative way. You can get the number and the kind of atoms. This was actually not possible until then. So here, this is work done at APS. So here they were looking at iron-reducing bacteria, just to show you the kind of things that you can do with XAFs. So they were looking at, I think this was sulfur, yeah, sulfur K-edge. It's not common to do sulfur because it's very low energy. We have here one beamline that does it, but it's very low. And well, they were able to, identify the path that these bacteria, I mean, the different structural changes that occur when these bacteria are actually doing their job. They're reducing the iron. So this is another example where this was done here at BM23. And this concerns looking at these trace elements in soil, in wetland soil. So we have a lot of this wetland soil all over our planet. And they play a very important role in sort of storing or sometimes even blocking these trace elements that can be toxic, like arsenic, for example, or mercury or lead and things like that. And so this is a group from Switzerland. They took some carrots. Carrots are long pieces of soil that they just dig out. And these were carrots that were 1.5 meters long. And they took samples from different depths. And they did a chemical analysis before coming to the beamline. So we knew, for example, that at this depth, they had this amount of arsenic, they had a little bit of iron, and they had a lot of organic matter. And what they wanted to understand is whether this organic matter has a role in blocking the arsenic. And if it does, how is this arsenic blocked in these organic molecules? So the experiments were not easy because you don't have much arsenic in soil. You have mainly carbon, nitrogen, but the data was very good, and they were able actually to identify exactly the bonding mechanism of arsenic inside these organic molecules. It goes through these sulfur groups. So we could very clearly see these 3 sulfurs. This is another example of work done at Swiss Light Source with a very small spot. So they were looking at spent nuclear fuel. And they were able to understand just from the xanes. So obviously this was very difficult experiments. The data is not great, but it's still sufficient to understand how these radionuclides are actually chemically bound to this waste material. Okay, and here I'll talk a little bit about high pressure science, because this is my area. So this is a nice experiment that we did many years ago on BN23. And actually, it had two different motivations. So on one hand, people are interested in looking at the reactivity of these rare gases, like xenon. Because normally, xenon, like all the other rare gases, they have a closed electronic shell. So normally, these elements are not reactive at ambient conditions, right? Because they have closed electronic shells. However, we know, for example, that xenon does react with oxygen at high pressures. And we know this because when you put xenon and you apply pressure, and in the diamond anvil cell, you add some oxygen, you see, for example, that the metallization pressure, at some pressure xenon will metallize. But if you have oxygen, this pressure changes. So you know that something changes when you put oxygen in there and you apply pressure. Also, if you do Raman with xenon and oxygen, you see that some peaks get weaker and weaker. So you know that there is some reaction going on, but you don't know exactly what. Now, there's been a lot of work to try to identify possible stable oxides of xenon around megabar pressures. And theoretical work, so this was a Nature Chemistry studying that. We did not do this. This is theoretical work that was done before. And they found many different kinds of stable oxides. But none of those have ever been observed experimentally. We will never be able to identify any of those. Now, why did people study this? Because the geoscientists are very interested in understanding why, for example, in the atmosphere of our planet, we have much less xenon than one would expect. Okay, so this is a big puzzle. They don't understand why. And one of the possible explanations is that when our planet was formed, xenon, it was very hot and very high temperature, very high pressures. Xenon reacted with oxygen, and now it's trapped inside the planet. So it's not in the atmosphere because it's inside our planet. So in order for that to happen, xenon must have reacted with oxygen. And so people are trying to understand these things. And so diffraction alone actually can see that there's a reaction. I don't know whether I show here. I don't show you here the thing. Well, with diffraction, you see very well that you see new peaks coming up when you put xenon and oxygen. But so you see that there is a reaction, but you don't know what kind of compounds are formed because xenon is a very strong scatterer with respect to oxygen. So if you do diffraction from something that contains xenon and oxygen, you only see the xenons. It's very difficult to see where the oxygens are actually sitting. And so we did xenon K-edge exafs in the diamond anvil cell. We heated with a laser. So you see before laser heating, this is what the xenon edge looks like. So you see you don't see any peak here. What does this mean? We were doing the K-edge of xenon at 35 keV. So we're exciting an electron from the 1s to something of p symmetry. So if we don't see anything here, it means that the p states are all occupied. There's no empty available state. As soon as you heat, you see a peak coming up. Why? Because the p states are depleted because you have oxidation. So that's how you see oxidation. So you see it on the exafs immediately, on the xanes immediately, by this peak that comes up. And you also see the exafs that changes completely. And what happens is you see this big peak that comes up. So if you don't laser heat, you only have one peak. And these are the xenon-xenon atoms. As soon as you pressurize and you heat, you see this huge peak coming up. And from here, you can really analyze that and get the exact positions of the xenon-oxygen, where the oxygens are. And so by putting everything together, the diffraction, this, and also theory, we were able to come up with the real stoichiometries, which were completely different to what had been predicted before. Then, this is the last example, so I'm even a little bit early. So this is a very nice experiment that we did on ID24 this time. And what did we want to do? Well, we were interested in, this was my interest. This is, again, high pressure. I've talked a lot about high pressure because this is what I used to do because I don't do much science anymore. But so what were we interested in doing? We were interested in looking at the properties of iron at very high pressures and very high temperatures. In a region of the phase space where iron is no longer a solid, it becomes what we call warm dense matter. So it becomes something which is not a solid, but it's not something that you can describe with plasma models because it's very compressed. So you have ions that are interacting a lot with each other, very strong correlation. So it's a state of matter which is too hot to be described by solid state models, and it's too dense to be described by plasma models. So it's this intermediate region where we don't have any good theory. So we really have to start doing measurements. And why is this important? Because this state here, at very high pressures and very high temperatures, is the state of matter inside large planets. Planets that are bigger than the Earth. The Earth, the center of the Earth is here, is at this pressure and temperatures of about 5,000 Kelvin. But we know, we've been discovering all these exoplanets, and these exoplanets on the average are much bigger than the Earth. So we expect, if we want to learn about these objects, we expect that the pressures in there will be much bigger than what we have here on Earth. And we want to understand the properties of materials or minerals or metals or whatever inside these very large planets because we want to understand, for example, whether they have a magnetic field. Do they have a liquid core like we do? Why is this important? Because if they have a liquid core, then maybe they have a dynamo, and maybe they can have a little magnetic field like we do on the surface of our planet. We have a little magnetic field very, very, very little, which comes from the fact that this metallic liquid is moving in the center. This outer core is liquid. And this little magnetic field actually has allowed us to be here. I mean, if we didn't have this little magnetic field, there would be no life on this planet. Because this little magnetic field is acting like a screen. It screens out all the cosmic rays that otherwise would have hit us and would not have allowed life to develop. So if we see, for example, one of these whatever 514XN planets that they find, they give it a name, and then we want to know whether maybe that planet hosts life or not. And since we will have very soon thousands of these, we have to be sure before we decide to focus on one of them whether, you know, it could be habitable or not. So it's really important to try to understand, you know, the properties of these objects doing experiments here. So to cut a long story short, we wanted to see the structure of iron. We wanted to look at the electronic structure and the local structure of iron in these really extreme conditions. We cannot reach these conditions statically, like by putting iron inside a diamond anvil cell and compressing and then heating with a laser, because the cell will break when we go to very high pressures. So we do this using a laser. So we come in with a very big laser. You see, this is our iron foil, which is a thin film, and then we sandwich it between two diamonds. The diamonds are there to confine this, the iron, and then we come in with a big, powerful laser. The laser ablates the surface. Here we put a little ablator, well, it ablates the surface of the target, which comes out in this direction. And for conservation of energy, momentum, etc., we have a shock wave that goes through the sample. And this shock wave heats and compresses the iron. Okay? And the diamond is there to maintain this very high pressure, high temperature state there for at least 1 nanosecond. We need at least 1 nanosecond to be able to measure it at the synchrotron, because our X-ray pulse is 100 picosecond. Okay, so we designed the target so that we can maintain a relatively constant pressure and temperature in the sample for 1 nanosecond. And we were able to do this. And then we go off with one single pulse and we measure the EXAFs. And we did it and we got very nice results. So you see here the data that you show here. This is the iron K edge at different pressure and temperatures. So each of these is a single measurement, single pulse. So the quality is actually very good, right? And when people saw this, you know, it made a really big splash in the synchrotron community, in the laser community. Everybody was really excited. And that's why now we have a big project here to bring a very powerful laser to do these experiments. So if you have the opportunity to visit ESRF, you should go on ID24. The laser is not there yet, but you can see the empty space. But if you come in 2 years, then you can come and do experiments. Actually, I hope that many of you will be interested in doing this stuff, because we need you guys, right? I'm getting very old. Everybody's getting old, and we need new people to come and do this stuff. So you see, you can get this with a single shot, and then you can analyze the data. You can see, for example, that you're going from BCC to HCP. So this is the transition that you see here, from BCC to HCP. And then this is HCP. So this was relatively, let's say, low pressures and temperatures. And then if you go to higher pressures and temperatures, you get this. So this spectrum here was taken here in this region. Okay? So what we see is an important shift of the edge. And interesting is that we are not able, I mean, our theoreticians, our colleagues, are not able to reproduce that shift. They see a shift, but they absolutely do not see the same amount. And since they were never able to measure it, they didn't know whether their theory was correct or not. So now they know that it's wrong, and they have to go back and do it again. But I mean, you know, that's when you start, and it's this really close interaction between the experimentalists and the theorists that really gets you somewhere at some point. So we're doing all we can to be able to measure this, even though it's not really good, but we can improve this, right? But just that shift was very important for them to get this information. So you see, this is a solid. You go to HCP, then you melt, and that's when you cross the melting point, and then you go. So the reason why these error bars are so big, because this was the first experiment we did, I think, in 2014. We didn't have a lot of diagnostics. So when you do this shock, you want to be able to measure the pressure, and you want to be able to measure the temperature. Otherwise, where do you put this spot, right? You can measure the spectrum, but if you don't know where you are, it doesn't help. And when we did that experiment, we didn't have in situ something to measure the pressure and the temperature. Okay, but normally we do have these things now. We can add them. So how do we measure the pressure here? We can measure the pressure using an interferometer in the back, which measures the speed of the shock wave from the back using an interferometer. It's called VISAR. And we can measure the temperature using very fast pyrometry. So all this is really complicated. I mean, you see, we were collaborating with many, many different institutes. These are big collaborations. And of course, we're just at the beginning, but I think that this has a lot of potential here in a place like the ESRF. And we also do these experiments now at XFEL, because there we have a lot of lasers as well. So I will talk a little bit about that tomorrow, because I'm also giving the talk tomorrow about XFELs. So I'm finished, even a little bit early. So I just wanted to tell you that maybe I went a little bit fast. I'm really sorry. I mean, especially in the part where there was a little bit of math, I saw that some of you were lost. But if you're interested, you can go and look at the appendixes and everything. It's really step by step. You can follow everything, and normally you should catch up. If you need more information, you can go on these websites. So a lot of this training material, I mean, especially some of the slides at the beginning, I took from these websites. Some others come from my PhD thesis. Others I made them during the years. Here's where you can find the software I talked about. So all those codes, you can go there. And here are books, again, for the different software codes that people use nowadays. And there's many more that are not included. Maybe I should do an update. Here you will find practical things. And as I said, at the end, you see, this is stuff that I took from my thesis, I think. And you can get all these, everything you need. So I'm finished, and if you have other questions, I'm here for a few more minutes, and then I'm back also tomorrow. So.